Okay, so in this video we'll go over an autonomous differential equation example. In this example we have a force of 10 newtons will hold the spring stretched at 5 meters. And I'm going to actually kind of show, here's a spring stretching something 5 meters. Suppose 4 kilogram mass, and this is the kilogram mass in this diagram, is attached to the spring. It is stretched to 5 meters, which kind of already wrote there. I'll also make this note of at 5, there's a force of 10 newtons holding it. When it's stretched to 5 meters and released with an initial velocity of 0 meters per second, so initial velocity 0 meters per second, and we are assuming there's no dampening. So that would bring us, if we look at stuff involving force, we essentially have this equation here. We have force plus a damping force plus the stiffness. We are already saying the damping force is 0, but the equation for that I'm going to at least write down first. And you may remember its force is mass time acceleration, which is just the second derivative of position, which we're going to use as y, which you could also see in this problem. That's what we want to call y, is the position, plus the damping force, which is some constant times the velocity, which again we know is 0, but I just want to write the equation, plus the stiffness, which involves the spring constant times the position, and then that will equal 0. Again, we were told damping force is 0, so we essentially just have this equation here, and y double prime plus ky equals 0. But we were also given stuff in velocity, so there's also kind of a hint in this problem where it says rewrite essentially in terms of velocity and position. So what we want to do is write it in terms of velocity and position. And before I do that, I just want to make one more small note that in addition to the initial velocity, we also know the initial position. The initial position at t equals 0 is 5 meters, right? Because it's stretched 5 meters from the equilibrium in the middle there. So, that being said, we can let v be equal to y prime, which makes sense because that's velocity, which then in turn means v prime is just y double prime. But before I write that, I'm also going to write y prime as dy dt. The reason being is because, well, v prime is y double prime, but if you rewrite it using the chain rule, that actually would be dv dy times dy dt, because we're using essentially v of y and y of t. We have to use the chain rule in that regard. And a nice reason to write it like this is because actually dy dt right here is just this, right? Which is y prime, which is just v. So what we can actually do is just write this as v times dv dy, right? That is nice. Why is that nice? Well, let's go back to our equation here and plug in a couple of things. My double prime, well, that actually is v prime, right? Let me write that a little nicer. So I could just write that as V prime right below. The mass is a 4 kilogram mass, so I can write that now, right? And after that, well, we know the dampening force is 0, so I mean, I guess I could write plus 0 just to keep space aligned, but you don't have to. And then the spring constant times y being equal to 0. Now, we essentially have it in terms of v and, well, v prime and y. We need to solve the differential equation, but we totally can do that now. Rewriting that, because v prime is actually just v times dy or dv dy. So it's 4v dv dy plus ky being equal to 0. And now we have a separable equation, essentially. We do need to find the spring constant, which we can. The spring constant is just, we find it by the force, mass times acceleration, minus the change in the, or minus ks being equal to 0, where s is the change in spring length. And we know those values. Force, there's a 10 Newton force that can hold it, so 10 minus k times 5, 10 Newton force holding it 5 meters away, so, and then that's equal to 0. And solving that, we get 10 being equal to 5k, k being equal to 2. So what we have is a differential equation for v times dv dy plus 2y being equal to 0. And I'm just going to box that. We are not done, but that is a nice differential equation we have, and we can solve it. Also, keep in mind, I'm going to kind of write here, v of 0 is 0, and y of 0 is 5, because we'll need that in a little bit. Notice I already kind of cleaned it up a little bit to save a little bit of time. Although now I'm regretting it because I would have to plug in that v prime again. I'm actually going to erase this, but we do see that this is a separable equation, and we can work on that right now, right? We can move the y terms to the right side. We'll have 4v dv dy being equal to negative 2y. Again, move the dy to the one side. We have 4v dv being equal to negative 2y dy. Variables are separated. And we can integrate, getting 2v squared being equal to negative y squared plus a constant c. And then now you can probably see why I wrote those initial conditions up here, so I wouldn't forget what they were. Velocity at t equals 0 is 0, and position at t equals 0 is 5 meters from the equilibrium, right? So we can plug those in order to get our c. Again, v of 0 is 0, so we know this is just going to be 2 times 0 being equal to negative, at t is 0, y is 5, so it's going to be 5 squared plus a constant, and we get 0 being equal to negative 25 plus c. c is 25, and that pretty much does it for us. All we need to do is plug in that c. We get 2v squared being equal to negative y squared plus 25. And there is our solution Although it does probably look nicer if we move the variables on the other side and write it as 2v squared plus y squared being equal to 25. And that is the solution to our differential equation.